Okay, let's jump right into this explainer. If you've been following the evolution of Web3 at all, you already know that Ethereum absolutely changed everything. It took the fundamental innovation of blockchain and asked a massive question. What if this wasn't just a ledger for money? What if it was a computer? Today, we're going to bridge the gap between high-level Ethereum theory and the actual under-the-hood execution of smart contracts.
Here's our agenda for today. We'll be hitting 6 key areas: the global programmable computer, inside the EVM, gas, the anatomy of smart contracts, the state transition machine, and finally, we'll actually simulate a smart contract.
All right, let's kick things off with Section 1, the global programmable computer.
There is just a stark contrast between the two absolute titans of the crypto space. Think about Bitcoin for a second. It was brilliantly designed as a static payment network using the unspent transaction output, or a UTXO model. It tracks discrete chunks of digital gold. Ethereum, on the other hand, it introduces a dynamic account-based programmable network. It's not just tracking balances, it's tracking the live state of autonomous applications.
So, the crucial takeaway here is that Ethereum is a Turing-complete network. As the Ethereum yellow paper outlines, this means it's capable of executing complex, deterministic cryptographic scripts. Basically, given enough resources, the network can compute absolutely any logic you program into it. It is, quite literally, a global, decentralized computer.
Moving right along to Section 2, inside the EVM.
To understand how this global computer actually runs, we have to pop the hood and look at the engine, which is the Ethereum Virtual Machine, or EVM. It operates in a strictly sandboxed environment. It relies on a stack-based architecture using 256-bit wide words. Now, that specific size wasn't just chosen at random, it perfectly accommodates Kekok 256 hashes and elliptic curve cryptography. The stack is limited to 1,024 elements operating on a last-in, first-out basis. This right here is the isolated, highly secure runtime where your smart contract's byte-coded instructions are executed by thousands of synchronized nodes all around the world. Inside the secure environment, a virtual ROM stores the immutable program code. When a contract is triggered, this code gets copied into the main memory using a specific opcode, and then the EVM's program counter reads and executes it step by exact step. Every single node on the network computes this exact same state output, which is what ensures total global consensus. Section 3. Gas, fueling the network. Here is the multi-billion-dollar question. How does a shared, decentralized infrastructure prevent infinite computational loops from crashing the entire system? Like, if it's Turing-complete, what stops a bad actor from running a program that literally never ends? The answer is gas. Gas is the elegant solution to the halting problem. It makes sure every single operation on the network is metered and paid for. Whether you're moving funds, modifying contract storage, or executing some complex math, there is a universally agreed cost in units of gas. If your transaction runs out of gas before the computation finishes, the EVM immediately halts and reverts the state, totally protecting the network from denial of service attacks. Because these gas costs correlate to tiny, granular computational steps, they're paid in Wei. Wei is the absolute smallest foundational unit of the Ether cryptocurrency. To put that microscopic size into perspective, 1 Ether is equal to 10 to the 18th power Wei. That's a 1 followed by 18 zeros. This scale allows for incredibly precise pricing of computing power on the network.
All right, Section 4, anatomy of smart contracts.
Now that we have the engine, the EVM, and the fuel, gas, let's explore the logic actually driving the network. The absolute best way to conceptualize a smart contract is through the digital vending machine metaphor pioneered by Nick Szabo. A smart contract operates autonomously based on strict, deterministic conditional logic. You know, those if-then parameters, without needing any sort of middleman. You input value, the immutable logic validates the conditions, and it dispenses the result or asset automatically. And crucially, once it's deployed to the ledger, this code cannot be modified.
This underlying logic brings us right back to Ethereum's account-based model. On the network, there are 2 distinct types of accounts you need to know about. First, we have externally owned accounts, or EOAs, which are controlled by human users via private keys. Second, we have contract accounts, which are controlled exclusively by their compiled bytecode. Now, both have an Ether balance, but contract accounts have the added superpower of maintaining their own permanent internal state and getting triggered by incoming transactions.
Next up,
Section 5. The State Transition Machine.
So every time a smart contract executes, it doesn't just happen in a vacuum, right? It causes a shift in the entire network's global state. Ethereum is fundamentally a transaction-based state machine. Let's track the exact chronological sequence of a state transition. When a transaction initiates, the network first verifies the signature and the user's nonce. Next, it calculates the required fee and deducts it from the sender's balance up front. Only then does the EVM execute the code. If successful, the value transfers and the state mutates. Finally, any leftover gas is refunded to the sender. But if it fails, everything rolls back, though the miner still keeps the gas fee for the computational effort they already expended.
To manage all this crazy amounts of data, Ethereum utilizes something called the account storage trie. Unlike the immutable global record of transactions, the account storage trie updates dynamically. It actively tracks the mutating asset balances and the internal state variables of every single smart contract on the entire network, block by block.
All right, our final section, number 6, simulating a smart contract. Let's dive into our cyber laboratory here. To really grasp this, we're going to look at a production-grade Python simulation of a smart contract transaction complete with integrated EVM gas metrics. Under the hood, the execution logic is brutal and precise. Step 1. Does the caller have enough balance to cover the base gas cost? If yes, deduct it, trigger the state mutation, and update the ledger. If no, meaning if that caller's balance is even slightly less than the gas cost, revert the entire state change immediately.
Okay, let's actually run test case 1. We have a caller, we'll name them 0x user alpha. They are trying to execute a function to verify their identity in the contract, but they only have an account balance of 15,000. Now, our simulated EVM requires a standard intrinsic gas cost of 21,000 per operation. So, what happens?
Boom! This immediately triggers the EVM's primary defense mechanism. The output is an out-of-gas exception. The transaction is instantly reverted. Absolutely no state is mutated, the ledger remains totally unchanged, and the network is protected from computing a transaction that simply can't be paid for.
Now let's run test case 2, but this time with a properly funded user, 0x user beta, who has a balance of 50,000. The pre-execution gas verification passes with flying colors. The EVM deducts the 21,000 gas cost. The execution succeeds. The contract's internal state database is permanently mutated so that the identity_verified key now equals true, and the color's remaining balance is accurately updated to 29,000. This exact micro-mechanism we just ran through, that is what is powering billions of dollars in decentralized finance every single day.
As we wrap up this explainer, I want you to step back for a second and just consider the immense power of this infrastructure. You're no longer just interacting with a static payment ledger, you are engaging with a decentralized, globally synchronized virtual machine. With a Turing-complete deterministic computer at your fingertips, what immutable logic will you deploy next? Thanks for learning with me today, and I'll catch you in the next one.